Hello, welcome back. So let's take a look at normal distribution. Now, first of all, why normal distribution? Who cares about normal distribution? Well, it turns out that normal distribution is actually one of the most important parts of statistics. The reason being that normal distribution is actually very close to real life, right? So when we look at real life situations, we notice that a lot of things in real life follow normal distribution. So stuff like heights, IQ, temperature. So what I really mean when I say that they follow normal distribution is that in real life, most of the data is grouped around a short specific range. So let's say I talk about IQ. Most of the people will have IQ within a certain range. Let's say 0 to let's say 100 to 120, right? And at both of the extreme ends there will be very less people, so the graph will look something like this. The probability density graph will look something like this. Most of the people lie within this range, right? And very few people lie on this extreme end and lie on this extreme end, right? And we notice this in a lot of situations in real life, and that is why normal distribution is pretty important. Now, we use normal distribution primarily for continuous random variables. What is CRV? Well, CRV is basically any data that is not discrete, that you cannot count in steps. So for example, speed is a continuous random variable. When we look at speed, we don't really see that, if there's a car that is constantly accelerating, it's not the case that at certain interval it's traveling at 1 meters per second, and then it suddenly jumps to 2 meters per second, and then suddenly to 3 meters per second. If a car is accelerating, what is really happening is that its speed is increasing continuously, right? It's increasing at every point. So that is continuous random variable. However, it is also to note that even though normal distributions are for continuous random variables, however, sometimes even though a distribution might be for discrete random variables, so for example, let's say x is some random variable that follows the binomial distribution where n is 300 and probability of success is 0.3, let's say, right? So even though this follows a binomial distribution, we can actually approximate this as a normal distribution. Why would we do that? Well, let's say I want to find the probability that x is greater than equal to 100. Now the problem with computing this is that it's very tedious. It's a very long computation, right? And if I somehow approximate this as a normal distribution, it will be easier for me to find the area under the graph, which is just the probability, right? So normal distribution is for continuous random variable. However, for other distributions, which may be for discrete random variables, I can make an approximation, right? So normal distributions has two parameters. The first one is the mean mu, and the second one is the variance sigma squared, right? So if I look at any normal distribution curve, let's say something like this, the only way I can change this is if I change this mean, or if I change how spread out or squished in the data is. In other words, the variance, right? So the parameters of a normal distribution are the mean and the variance. And so if I want to convert this binomial, this distribution, into a normal distribution, in order for me to approximate it like that, I will first find its mean and then I will find its variance, and hence I will have the normal distribution. Right, now let's come to the computational part. How do I calculate the probabilities of normal distribution? Right, so first of all, you would need to understand that actually finding the area under a graph that follows normal distribution is actually pretty hard. Its formula looks something like this, and it is very hard to integrate this. So we sort of took a backdoor way, and Cambridge provided us with a set of values that we must learn how to use. Right, so first of all, let's look at the z-curve. The z-curve is a curve that is normally distributed, and its mean lies at 0 and it's of variance 1, and so it will look something like this, right? So my maximum value is reached at the value 0, this which is my mean, and the variance is 1, right? Now what is this? This is actually the, okay, let me write z over here. This is the probability density function of this, and so what I'm really saying is that the area under this curve gives me the probability up to that point. So for example, oh, and one more thing, this curve goes from negative infinity all the way to positive infinity, right? So if I'm looking to the left hand side, the value gets closer and closer to 0, and it stretches on to negative infinity, and if I look on to the right hand side, the curve also gets closer and closer to 0, and it tends to positive infinity, right? So if I take some point, let's say z equals 2, right, and I find the area up to that point, what I will really be doing is that I will be finding the probability of z being greater than or equal to 2, which can basically be written as something like this, right? So finding the area under the graph up to that point will give me the probability of z being less than equal to, this should be this sign, right? So it's the probability of z being up to 2, right? Similarly, if I write something like -2 and I find this area, this will basically be the probability that z is less than or equal to. And by the way, in a continuous random variable, for a continuous random variable, if I write something like z less than equal to, or if I write something like z less than 2, these are basically the same thing, because probability of a single point is basically 0 in a continuous random variable, right? So now there are basically a few properties of this curve that we essentially use in our favor. So the primary property of this z curve is that it's a pretty neat curve. It's a symmetric curve, right? So what I really mean by that is that, let's say I'm at this point and I take a look at 2 units to the right and 2 units to the left. So I'm looking at z equals 2 and I'm looking at z equals -2. Now when I say that these are symmetric, what I really mean is that the probability or the area from 0 to 2 is equal to the area from -2 to 0, right? So the area from 0 z to 2 is the same as the area from -2 to 0, right? And the reason why this is the case is that its mean is 0. Its mean lies on 0, and this curve is symmetric, right? So now also notice that if I take the area from negative infinity to positive infinity all the way, it will actually be 1, right? The reason being that since area under the graph represents the probability, and if I am finding the area from negative infinity to positive infinity, I am adding up all of the possibilities, I am adding up all of the probabilities. So adding up all of the probabilities will actually give me 1, right? So area under this entire curve will actually be 1, right? And so we can basically conclude one property of this, that the area up to z is the same as 1 minus the area up to -z, right? So what I really mean by this is that, let's say this area is the same as, if I draw the same curve over here, okay, let's draw it over here. If I draw the same curve over here, that area, this is -z, is equal to this area, right? So if I take a look at this, if I take the area from negative infinity to z, it is the same area if I take the area from positive infinity to -z, right? Because it is symmetric, right? And also just one little short thing, this half will be 0.5 since the curve is symmetric and the whole curve, it has the area 1, so halfway through it will have the area 0.5, right? So essentially, if I want to find, let's say, if I want to find the z value, this will be some negative value. If I want to find the z value that has this certain area, that will be equivalent to me finding this. Okay, so if this is negative z, this is positive z, it will be equivalent to me finding this area and then putting a negative over there, right? So if I have any probability that is less than 0.5, my z value will be a negative value, and any negative value, if I want to find it, it could be the same as me finding this area, which will give me the positive value and then making it negative, right? So let's take a look at this table over here. Now what I told you that, it's integrating this curve is actually pretty hard, and so what we have really done is that we've taken a look at the z curve, which is a standard curve, and Cambridge actually has given us different values, right? So it has given us a table from which we can read out the z value and we can point out the area up to that point, right? So these are, the table gives the value up to that point z, right? And okay, so this should look something like this, up to that point z. And in actuality, if we know the area for this standard curve, we will actually know the area for any distribution that follows a normal distribution for any mean and variance, right? So if we somehow got the area considering our standard z curve, we can use it to find the area for any other normal distribution, right? So let's take a look at how to read values from this table. So let's say I have my normal distribution curve and I want to find the area up to, let's say, 0.423, right? So I want this area, or in other words, I want the probability of z being less than equal to 0.423, right? So first of all, I look at these values, and these are basically the values of z up to 1 decimal place. So up to 1 decimal place, my value is 0.4, so I will mark this. Right, now my second decimal value is 2, so I will mark this, and I will see where they intersect. Right, so where they intersect, they give me the value 0.6628. Right, now I am left with this 3. I will look at this column. Right, so for the third decimal place, I am looking at this add column, and I am looking at where it intersects this. It intersects this at 11, so I will add 0.0011 to this, which gives me 0.6639, and this is my answer. So the probability of z being less than or equal to 0.423 is 0.6639. Right, so all I did was first look at my first decimal place and then the second decimal place and see where they intersect, then look at the third decimal place and the first decimal place and see where they intersect, and then add them up. Right, now you will find one slight problem in this graph is that the least value that it takes, the least value that it tells us is 0.5, and what's really happening here is that we know the areas for anything that is to the right of 0, right? But we talked about this before, that how in the standard normal distribution curve, if we know the positive value, we can simply calculate the negative value too. So for example, in my normal distribution curve, let's say I want to find the probability that z is less than or equal to, let's say, negative 0.423, right, taking the same number. Right, so here I found the area of being up to 0.423. Now I actually want this area, negative 0.423. Right, So if I look at my curve, okay, so I already drew it here. So if I look at my curve, I know what the area up to 0.423 is, and I need to find out what the area up to negative 0.423 is. Right, in short, I need to find this area. Now notice that since this curve is symmetrical, this whatever this area turns out to be will be the same as whatever this area turns out to be, right? And we already know what this whole area is, and we also know that the entire area is 1. So if the entire area is 1 and the area up to the left of 0.423 is 0.6639, then subtracting 1 from 0.6639 will give us this area to the right of 0.423, which is also equal to this area to the left of negative 0.423. Right, so essentially what I really did was that the probability of z being less than equal to negative 0.423 is the same as 1 minus the probability of z being greater than or equal to probability of z being less than or equal to 0.423. Right, so generally the area for any negative z is the same as 1 minus the area up to z. Right, so essentially we use the same idea in some other ways, but this would be the same general idea, and you would be using the same thing over and over again, essentially using the property that it's symmetric and using this to find other values of z. Now if we know the area up to z, how do we relate it to some other normal distribution? So let's say x follows some normal distribution such that the variance is, let's say, 6, and the mean is 6 and the variance is something like 3 squared. Right, so, and let's say I need to find the probability that x is less than or equal to, let's say, 3. Less than or equal to 3. Actually, let's say that x is greater than or equal to 3. Right, so the probability that x is greater than or equal to 3 is the same as 1 minus the probability that x is less than 3. Right, now this simple formula of finding the corresponding z value is the following: z equals x minus mu over sigma, where mu is the mean and sigma squared is the variance. So this would be the square root of variance, which is the standard deviation, and x is basically the value of which you want to find the z value of. Right, so here I want to find it up to 3, so let's say z equals 3 minus 6 over 3. This would turn out to be negative 1. What this really means is that here my distribution will look something like this, where this is 6, this is 3. If I'm converting it to my standard curve, it will basically be this value, which is negative 1, where this mean is 0. Right, so essentially I want to find the area up to x equals 3, which is the same as the area up to z minus 1, right? Because x being equal to 3 is equal to z being minus 1. So I want to find the area of z up to minus 1, which is basically this area. So now what I will basically do is I will find the area up to 1, which will be this thing, and then I will subtract 1 from it. Right, so this is equal to 1 minus the probability of z being up to 1. And what is the probability that z is 1 is basically, here is 1 and then my decimal place is 0, so 0.8413. Right, so 1 minus 0.8413 is basically 0.1587. Right, so essentially we got our answer. Right, we knew some we knew a curve, we knew something that followed a normal distribution. So we first converted it to our standard z curve, for which we know the values of, and then we calculate the probability, which in this case turns out to be 0.1587, right? And that's all for the normal distribution.